All materials, from rubber to wood to steel, undergo changes in shape and size when subjected to loads. These changes in shape and size are referred to as deformation of the material. Deformations in structural members may be significant and obvious, or they may be so small that they are unnoticeable. The measurable parameter of strain quantifies the amount by which a structural member or some part of that member changes its shape or size. Strain arises from stress due to forces, moments, and/or temperature changes. There are two main types of strain. Normal strain measures the deformation of a member subjected to a normal stress, and shear strain measures the deformation of a member subjected to a shear stress. Consider a member, shown below, subjected to an external normal force P. We can refer to this force either as a normal force acting perpendicular to the cross-section or an axial force as it lies along the longitudinal axis of the member. Prior to loading, the diagram shown at the top here, there is no deformation of the material. After loading, the member experiences an internal normal force N equal to P, and thus a normal stress sigma equals N over A. As a result, the member undergoes a change in length, which is being shown here in the bottom part after it has changed its length. Normal strain quantifies this change in length that arises from an applied normal force. Because normal strain is not necessarily uniform throughout the member, we generally refer to average normal strain. If the member has initial length L before loading and final length L prime after loading, such that it elongates an amount delta, then average normal strain can be defined as follows. Epsilon sub average, average normal strain, equals, on top, L prime minus L, and on bottom we have L. So on top we have the change in length, on bottom we have the original length. In this equation for normal strain, L prime minus L is equal to delta, as shown below. Given that a normal force can be either tensile or compressive, delta, the elongation, and thus epsilon average, average normal strain, can be either positive or negative. The sign on epsilon average is positive for cases of tension, causing elongation, delta greater than 0, and negative for cases of compression, causing contraction, delta less than 0. Thus, the general term for the quantity delta is displacement rather than elongation or contraction. Notice that normal strain, as it's defined, measures a change in length per unit length, and thus it is a unitless number, that is, a ratio of two lengths. It can also be expressed as a percentage or in units such as millimeter per millimeter, micrometer per meter, inch per inch, etc. Let's now define the other main type of strain, which is shear strain. Consider a member, shown below, subjected to an external shear force V. Prior to loading, there is no deformation of the material. After loading, the diagram on the bottom, the member experiences an internal shear force equal to the external shear force V, and thus a shear stress tau equals V over A. As a result, two reference line segments in the member undergo a change in angle between those line segments. Prior to loading, we have this scenario, this block fixed at the base. We have various line segments of reference, perpendicular line segments. After loading, after applying the shear force V, we see changes in the angles between those line segments. Shear strain quantifies this change in angle between two line segments in the member, which arises from an applied shear force. We generally refer to line segments that have an initial angle between them of 90 degrees or pi over 2 radians. If the final angle after loading is referred to as theta, then shear strain can be defined as follows. Shear strain, represented by this Greek letter gamma, is defined as pi over 2 radians minus theta. We're using radians here, which is equal to the initial angle between those line segments minus the final angle between those same line segments. Like normal strain, shear strain can be either positive or negative, depending on the value of theta. So notice from this above equation here, if theta is less than pi over 2, that is the angle decreases in size, gamma is positive. If theta is greater than pi over 2, that is the angle increases in size, then gamma is negative. Since angles are usually measured in units of radians or degrees, either unit can be used to express shear strain. For a review of concepts from chapters 1 and 2 and a preview of concepts from chapter 3, I highly recommend you to view the following YouTube video by the Efficient Engineer. You can follow this link here to view the video. It's about 10 minutes long.